So we start our presentation with introduction. First, what is flash separation? Flash separation is a process used to separate a liquid mixture into vapor and liquid by changing the pressure temperature of both. During this process, the more volatile component changes into vapor, while the less volatile components remains as liquid. This separation is based on the principle of vapor-liquid equilibrium, or VLE. Now let's look at the industrial applications. Flash separation is commonly used in petroleum refineries, petrochemical plants, solvent recovery system, and chemical manufacturing. It helps separate light hydrocarbons from heavier ones before further processing, making industrial operations more efficient. So our assigned mixture is hexane and octane mixture. Hexane has a boiling point of 68.7 degrees Celsius, while octane has a much higher boiling point of about 125.6 degrees Celsius. Since hexane is more volatile, it vaporizes more easily than octane during flash separation. As a result, hexane is mainly found in the vapor phase, while octane remains mostly in the liquid phase. This difference in volatility makes the hexane-octane mixture suitable for flash separation and for our vapor-liquid equilibrium calculations. So next are the objectives of our project. The first objective is to review the operating conditions of the hexane-octane mixture. The second one is to perform flash calculations by assuming the mixture behaves as an ideal solution. We also determine the vapor and liquid compositions at equilibrium and finally analyze the separation results.
Now I will present the process and composition conditions used in our flash separation. The feed basis is 100 mol per hour, consisting of an equimolar mixture of 0.5 mol hexane and 0.5 mol octane. The flash separators operate at 90 degrees C and 101.325 kPa. This operating temperature is selected because it is between the boiling points of an hexane and an octane. At this temperature, an hexane vaporizes more readily while an octane remains mostly in the liquid phase, allowing the separation to occur. Next, for the assumption. Firstly, an hexane and octane mixture behaves as an ideal gas solution. Second, Rod's law is applied for vapor-liquid equilibrium. Third, feed consists of only an hexane and an octane is a binary mixture. Fourth, flash separator operates under steady state condition. And lastly, a feed basis of 100 mol per hour is assumed for material balance calculation. So this is our overall PDF for the flash column. We have inlet stream, which is octane and hexane mixture, and outlet stream, which is top stream, hexane and octane in a vapor phase, while bottom stream, octane and hexane in a liquid phase.
I will now present the flash calculations for the hexane-octane separation process. The flash calculation was carried out using an equimolar feed consisting of 0.5 mol fraction of hexane and 0.5 mol fraction of octane, with an operating temperature of 90 degrees Celsius and a pressure of 101.325 kilopascal. For this analysis, the mixture was assumed to behave as an ideal solution, allowing Rod's law to be applied throughout the calculations. The first step was to determine the saturation pressure of each component using the Octane equation. The calculated saturation pressure of hexane is 189.02 kilopascal, while octane has a saturation pressure of 33.50 kilopascal. Since hexane has the higher saturation pressure, it is more volatile and therefore vaporizes more easily than octane. Next, the equilibrium constants or K values were calculated. The K value of hexane is 1.8655, which is greater than 1, indicating that the hexane preferentially enters the vapor phase. In contrast, the K value of octane is 0.3306, which is less than 1, showing that octane tends to remain in the liquid phase. The flash calculation then determined the equilibrium phase distribution. The calculated vapor fraction is 0.1692, corresponding to 16.92 mol per hour, while the liquid fraction is 0.8308, corresponding to 83.08 mol per hour. This confirms that only part of the feed is vaporized, allowing vapor-liquid equilibrium to be established inside the flash separator. Finally, the equilibrium compositions were determined. The vapor stream contains 81.36 mole percentage hexane and 18.64 mole percentage octane, whereas the liquid stream contains 43.61 mole percentage hexane and 56.39 mole percentage octane. These results clearly show that the flush separator enriches the more volatile component hexane in the vapor phase while concentrating the octane in the liquid phase. This demonstrates that the flash separation process performs as expected based on the principles of vapor-liquid equilibrium. Thank you.
I will now discuss the result obtained from the flash separation calculation. Based on the calculated result, the flash separator successfully separates the hexane-octane mixture according to the difference in volatility between the two components. Hexane has a higher saturation pressure and equilibrium constant than octane, making it more volatile component. As a result, hexane vaporizes more readily and becomes concentrated in the vapor phase, while octane remains predominantly in the liquid phase. The results also show that the vapor fraction is 0.1692, which is 0.1692, which means only 16.92% of the phase is vaporized while 83.08% remains in the liquid phase. This indicates that partial vaporization has occurred, allowing both vapor and liquid phases to exist simultaneously inside the flash separator. Such conditions are essential for establishing vapor-liquid equilibrium, which is the fundamental principle behind flash separation. Furthermore, the equilibrium composition confirms the effectiveness of the separation process. The vapor stream contains 81.36 mole percentage hexane, whereas the liquid stream contains 56.39 mole octane. This clearly shows that the flash separator enriches the more volatile component in the vapor phase while retaining the less volatile component in the liquid phase. These findings are consistent with the expected behavior of the hexane-octane system under the selected operation. Overall, the result indicate that flash separation is an effective primary separation method for this binary mixture. Although a single flash separator cannot achieve complete purification, it significantly improves the separation before further processing. This can reduce the operating load on downstream distillation columns, leading to improved process efficiency and lower energy consumption in industry application. Thank you. That's all from me.
Conclusion for this project: objective of the flash separation study were successfully achieved, which is hexane was enriched in the vapor phase while octane remained mainly in the liquid phase. Flash separation proved effective due to the volatility difference between both components. Vapor stream contained higher hexane composition, which is 81.36 mole percent, and liquid stream contain higher octane composition, which is 56.39 mole percent. The process can reduce the load on downstream distillation and improve efficiency, and also flash separation is suitable as a preliminary hydrocarbon separation process. Recommendation for our project: first, we can increase operating temperature carefully to improve vapor formation and separation efficiency. And next, we can use multiple flash separation stage for better purity of hexane and octane. And also we can apply real industrial operating data for more accurate analysis, and we also can consider non-ideal solution behavior for future studies instead of assuming ideal condition. And also we can improve energy efficiency by integrating heat recovery system in the process. And for the last, we can conduct economic and safety analysis before industrial scale application for this project. That's all from me. Thank you.